Ben je niet goed? Shall we continue?
Let's go.
Excellent. Excellent. I want to shift gears to the other important mechanism of light-tissue interaction, namely scattering. So not just sticking with absorption, but now also looking at scattering. And you will see in the first bullet point that that we will use the same kind of metrics to describe that interaction on a fundamental basis. So again, an efficiency, again a cross-section, and again a coefficient. But we'll get there. I want to start out with basically a short virtual walk outdoors. This joke was a little bit more sad in the days of the pandemic, because now we could actually do that. But, we'll go through the scattered field, scattered intensity, then we'll get to calculating the scattering cross-section, and then in the end we'll define some new functions, some new way of describing light scattering with the phase function. I loosely defined scattering earlier on as just the deflection of light, the change of the direction of light. And just like absorption, we can describe this process using the quantity scattering efficiency, scattering cross-section, and scattering coefficient. So the definitions are quite analogous, as you can see. So the scattering efficiency is basically the ratio of the scattered power divided by the incident power, and thus is dimensionless. The scattering cross-section, by the manipulations that we did before, is then the ratio of the scattered power over the incident intensity. You can figure out how that works with the relation to the geometrical cross-section by now. And as you can see by units, by comparing the units, it works. And then the scattering coefficient is defined here as the sum of the scattering coefficient of all the particles divided by the total volume V. So this looks a little bit different than what we had before. But if you realize that so what were the let's turn it around. What were the equations that we had before for the scattering coefficient? For the absorption coefficient, that was of course in that case.
Mu is rho times sigma.
Yeah, so mu is rho times sigma, and rho, that was in for rho we had a slightly different way of writing it than is equal to Fv, so the volume fraction of the particles divided by the volume of one particle times the sigma A. But of course, there was this relation between the volume of one particle and the total volume that accounts for this. So the only thing that was a little bit implicit here is that all the particles had the same absorption cross-section in this case. This is a little bit more general in the sense that you can that we can allow here that that the scattering cross-section for individual particles can be a little bit different. Okay. You can verify. So the fun questions. So why is the sky blue? Why are clouds white? Why is the morning sky or the evening sky look red? Let's go through them one by one. just shoot if you have a good explanation, that is even better. So part of it is of course already here.
Sorry, can you repeat the question?
So why is the sky blue?
Oh, is it not because blue sky is scattered more than blue light is scattered more than red light?
Yeah, that's exactly true. But then the follow-up question is by what particles? The answer is already there, so it is not.
The atmosphere.
Yeah, so in the atmosphere has these small particles, these tinier than water drops, let's say, so airborne molecules.
Oh,
That,
it's a bit there.
yeah, that's good. Yeah, so I'm sorry, that was a little bit too fast, but clicking through.
Why is the blue light specifically scattered more efficiently?
Yeah, we'll get to that a little bit later.
Okay.
So first I'll do the phenomenology, and then there is a physical explanation for that as well. Yeah, so basically what you see is that if you observe the sky away from the sun, then you're not looking at direct light. So direct light would be looking at the sun, which I do not recommend, of course. So whatever light is scattered more efficiently from out of the line of sight, in yellow, is what reaches your eye. So that's why the sky appears blue. If you would look directly to the sun, of course, then it would appear white. So what was the next question? So why are clouds white? So clouds you can look at without any home tools. So why are clouds white?
They absorb all the scattered light.
Yeah, but
Oh,
of course they do, and so here we had the situation where we know that blue light is scattered more efficiently from these molecules. And it's basically expressed in that equation. So the absorption coefficient is going to be proportional. It's a little bit hard to see, but it's going to be proportional to lambda to the power -4. So blue light, which has short wavelengths, is much more efficiently scattered than let's say red light. But now back to the other question. Why are clouds white?
act more like an inverted person.
Yeah, that's okay. You had an. Yeah, and that's so your answer is not wrong, but I was looking a little bit more along an answer in this ways. So here you can see a very distinct scattering dependency on the wavelength, and for clouds. So what are clouds composed of? Water particles, yeah. So they tend to be bigger, much bigger than these molecules, and they basically scatter more efficiently. That was the cloud. So it can get even more complicated. So if you would look at, for example, the horizon at daytime, so far away, then. So strangely enough, if you would look starting from the zenith, from where the sun is onto the horizon, first you would see blue skies. But if you look further and further, it gradually gets more whiter. So that means that all the other colors are basically scattered in the end more efficiently back to your eye. That is the detector in this case, and that can be a lot of things. That can be due to the surface. That can be due to light so here moving to a faraway distance, a lot of blue light is removed. So far away at the horizon, there is not much blue light not much blue light left, but when it travels then to your eye, that little bit of remaining blue light is also scattered away. So in the end, you end up with more visible colors. So it is a complicated interaction between the wavelength, the particle size, and the geometry that you look at things. And that is basically the point that I want to make, that we also have in tissue. There was one. It's the slides for the clouds. So water molecules, like you said, or water particles, they tend to scatter light much more efficiently. So here the scattering coefficient would scale with the lambda, the wavelength, to the power of well, let's say -2 instead of -4. So that is a much more gradual decrease. So they would just appear more whitish. Yeah, red evening skies, that is also the same thing. You have a complex interplay between geometry and where the light and where the observer is. So if you would directly at the sun, a lot of blue light would be scattered away because that is done more efficiently in the atmosphere. So what you're left with in this case is red light. So that's why the evening sky then starts looking red. So if you now look at tissue, so this great interplay between wavelengths, between size of the particle that scatters the light, and also the geometry that is not evident from this picture. These are kind of the structures that we have in tissue that cause scattering signals. I'm not saying that we can measure them individually, but each of these structures has a size, wavelength ratios that could cause some of these effects. And that starts already at pretty small wavelength, so at about 10 nanometer. If you would have so nucleosomes would be of the size of 10 nanometers. Already visible light would be scattered by these small structures. That seems a little bit counterintuitive, for example, to the resolution of the microscope. But, so from there it would start, and then open to cells, of course, which can be 1 micrometer, or for red blood cells even much higher. So again, the question is that the same question that we had earlier on for absorption. At what scale should we describe now light scattering, absorption earlier on, and now scattering? So they are not they're in reversed order in this case. So from big to small, you could do a measurement where you shine a broad beam of light on a larger piece of tissue, and we get a response. That would be a response from the vasculature, for example. A much more microscopic, maybe even intravascular way of looking at responses would measure the red blood cell. But ultimately, physically, if you break it down, then you would be looking at single dipoles. So at what scale do we need to make our theories? Because the theory at this scale, and this scale is going to work very differently. Maybe one day it's unifiable, but it's gonna work differently. What I do want to do is start at the smallest scale, so at the dipole scale. But first. So if you start at the particle level, so that is not a vasculature, but maybe the cell or the red blood cell, and maybe the dipole. So let's so consider that as a particle for the moment. So let's start there. We'll transition into the dipole. So we have a particle where we can define or identify an area G again of the particle, so cross-sectional area, And we can simply use our equation that we have before. So the scattering efficiency is the ratio of the scattered power over the incident. Then the scattering cross section, just like we had with absorption, scattering cross section is the product of the scattering efficiency with the geometrical cross section, which we knew because we could identify that. That's great. And then if we scale up with sorry, first of all, we can identify the scattered power, or we can calculate the scattered power if we know the scattering cross-section of one particle and we know the incident intensity. And so remember, this has units of per square meter. This has units of watts per square meter. So if you multiply these two, you get the power. So this would be the total power that is scattered by, in this case, one single particle. Okay, so let's start with that equation. So now the question is, okay, how can we find the scattering cross section? The good thing about this question is that we, on the left and on the right hand side, we have two things that we could, in principle, measure. We could measure the total scattered power. We could measure the incident intensity. So there should be a way to calculate the scattered power. So what we'll do is place that particle in a hypothetical sphere with a given radius that we know, or a given surface area that we know, and we will calculate the scattered intensity just by a generalization of that equation that is over there. So not simply a product of the scattering cross section and the intensity. We will calculate how much of the incident intensity emanates from the surface of that particle, from the surface of that sphere that is around the particle, like that. The input product in the unit vector n, or there, just to say that you have to evaluate this perpendicularly to the surface of the sphere. Again, if you look at the units, if you would, dA would have units of square meters. Intensity, it has units of watts per square meters. So in the end, the integral makes it right. You would have units of watts in the end. So the recipe then is to get an expression for the scattered intensity first. So the intensity that is scattered through that surface. Then if we have that, then we can integrate that over that surface. We would have to find dA first, but that is a side step. Integrate over that surface, and then we can solve the equation above. And we can calculate the scattering cross section. So let's go. So here on top is the equation that we aim to solve, and in green the scattered intensity is the quantity that we need to would like to calculate. Just a brief look at the coordinate system, how this all plays out. So we have a particle here, confusingly in blue instead of in red there, at the center of a coordinate system. Let's have the light coming in at the direction of -z, so aiming at the particle, and it is scattered away at some direction that is given by the factor k scattered. It is illuminated with a plain electromagnetic wave of unit intensity, So we write that as E in of spatial coordinates R is a complex exponential of the wave number k times R over input R and then minus omega t for the oscillation. This is just a standard plane wave. Is this in any way unfamiliar? Because that's unfamiliar. It's familiar. So the magnitude, and then just to relate it back to physical properties. So the magnitude of the wave vector, so the absolute value of k in, would be k would be 2 pi over lambda. Lambda would then be the wavelength that determines the call. So it is really connected to the physical appearance of that wave. So now we have an expression for the incident intensity for the incident electric field that goes in still as a complex exponential. The amplitude is 1. That's an arbitrary choice. We can always scale that back, so not too much for that. What I'm just going to do here is now pose a very convenient form of the scattered field. And it's very convenient because it's very general. So I'm going to just write the scattered field as something that is still a plane wave, because we still have this complex exponential part at the end with the scattered wave vector and the omega t oscillation. Then there is a function s in the denominator of the prefactor that has an unit vectors in the scattered direction and unit vector in the input direction as inputs, and there is some scaling in the denominator that's not very important. That is just for normalization. But, so with and assuming that this general expression holds, then we can make a few assumptions and get to a meaningful result, because the first assumption is that we have elastic scattering, which means that the wavelength does not change. Furthermore, we assume that the scattering process is in phase, which means that we have this omega t time term in the incident field. We have an omega t term in the scattered field, and there is no additional phase differences. So it is in phase. It's instantaneous. It is immediately converted to optics. And that also implies basically that the scattered wave vector or the magnitude of the scattered wave vector is going to be the same as the magnitude of the incident wave vector. So there is no change at all. So now if you now look at that scattered wave in the far field, and that's eventually where we want to go, because we want to put this large sphere around it. Then in the far field, the scattered field is going to be a spherical wave. So and scaling with 1 over r. And then of course there is this one big unknown, and that is this function s, this complex redistribution function that describes how the amplitude and the phase of the light is redistributed from the incident direction into the scattered direction. So that's but that's something that we'll deal later with, because we can for now use the general expression.
Sorry, can I ask something?
Yeah.
If you go back, I don't exactly get what you mean with the spherical wave.
So the subscript S is missing here, but this is the outgoing spherical wave from the outgoing scattered wave from the particle, and because that so the particle is here, the scattered light is just emanating in all waves. So the amplitude of the field will decrease with 1 over r. The power will decrease with 1 over r squared.
Okay. Yes.
That is the
Thank you.
yeah, with the unit vectors that we had. So let's do so we can do a little bit of manipulation with these two expressions. So again, the assumption was for the incident intensity that it was just a plane wave that hit the particle. The second assumption was that we can write a general expression for the scattered field, and the third assumption is that it's in phase, so there is no color change and there is no time difference. So we can then manipulate that a little bit. We know that the case or the amplitude of case for the two waves are going to be the same, so we can express them in terms of their unit vectors, like over there. We can arbitrarily place the particle at the origin and make the input intensity a scalar function. There does not need to be any complicated spatial dependence on that. So then we can start to simplify. So first here we can the incident intensity, so that's the top equation, has now no R dependency anymore. That is not entirely obvious from that argument I see now, but okay. That becomes a complex exponential that depends on the spatial coordinate and on the temporal coordinate. So we can split that. We can do the same thing for the scattered field. So this function remains there. This normalization remains there. But here too, because the case are the same, we can now safely split it into a temporal and in a spatial component. So these are basically two equivalent expressions for the two that you see on top. Yeah. So on the one hand side, we have this generalized incident electric field. On the other one, we have the generalized scattered field that goes out. Now, of course, the easiest way is to isolate this temporally oscillating part. There was no phase difference. There was no temporal difference between the incident and the scattered field. So we can isolate this one and then combine it. Combine that expression with the term in the scattered field, so that we only end up for the scattered field with spatial components. So that would then look like this. So again, you would have you would now have the general expression for the scattered field with the function s, with an exponential part that depends on the scattered wave vector, and now with the complex part of the incident wave vector replaced by the conjugate. That would be yeah, and then of course you can combine that into something that has basically. So now on the right hand side, we now have something that is a function of the unit vector in the scattering direction, the unit vector in the incident direction, and an exponential that has the difference between these two unit vectors. So that may not make that much sense yet, but mathematically that is really convenient, as we'll see. Now, of course, the electric field itself is not something that you can measure. It would oscillate too fast, and it is quite a complex terminology. You can already see it. So we need to measure the intensity. The intensity is the square of the electric field. More formally, it is the product of the complex electric field with its complex conjugate. And then you can take an amplitude for what is worth. This is what would calculate the measurable quantity, the measurable intensity. So if you apply that to the if you would apply that to the scattering equation, we would so whenever there is a complex term, we would take its conjugate and multiply. whenever there is a scalar term, we would just take the square. So for the denominator, you would get k squared r squared. For the s function that we still have not defined yet, would be s times s star times its complex conjugate. And the good thing is that all the spatial complex terms just vanish. So taking the complex conjugate in this case would just mean replacing the minus I plus with the plus I. So these terms, these spatially oscillating terms are now gone. They are finished. So the expression for the measurable quantity simplifies to this. We don't know yet what the function S is. It could be a complex function, it could be a scalar function, so or a real function. But let's assume that it has some kind of general form, so with an amplitude and a phase term, exponential missing there, I see. Then again, if we take the complex conjugate, then the exponential terms drop, and it simplifies even further to an expression like this. So this would be an expression for the scattered intensity in the direction of the scattering. So the SC is a unit vector in the direction of scattering. R tells you how far away you're looking. This is the incident intensity. The k squared times r squared tells you that we're looking at a spherical wave. And then the S function remains to be determined. Yeah, so that's
Is S the end? Can we say that? So the S dependent on SC and or
that depends a little bit on which S you mean. This one or
the
that one.
the black one.
The black one would be an amplitude. Yeah, this would be a general complex quantity, which could have an amplitude and a phase. But by splitting it like this and then taking the square, we get rid of all the phase terms.
So the amplitude is dependent on SC and
On the direction. Yeah.
So that's still the same intensity that we talked about previously, that being power divided by area.
Yeah. Absolutely. That is still the same intensity, and that is the one that we needed to fill in one of the previous equations to get to the scatter power and to get to the scattering cross section. Yeah. So that is still the same. Yeah, so far, let's run over it briefly. So we started out with the general expression from the definitions of the scattered power being equal to the scattering cross section times the incident intensity. The goal was then to measure numerically the scattered power and divide by EN, then we would have an expression for the scattering cross section. The scattered intensity through the surface of a sphere can be calculated by, so the one that you have to put in can be calculated by taking the scattered intensity and then filling it into that integral and solving that. And what we did until a few slides ago is derive an expression, a general expression for the scattered intensity. Yeah, so this was the recipe, and the result of the first step, get an expression for scattered intensity is shown over there. So with all the complex and all the phase information removed, it is just now something that is measurable. Yeah, so the second step is also a little bit tedious because this we have to do this integration over a spherical surface, and that is usually not best done in spherical coordinates in Cartesian coordinates, but in spherical coordinates. So we're going to have to look at a little bit of manipulation as well, again, to change this integral into something that we can actually work with, that we can actually calculate. So let's go. Again, the coordinate system that we're looking at is the particle is placed at the center of the coordinate system. The incident light is along the unit vector along the minus z axis, and the scattered light can be any direction. That is free, of course. But if we look at not only a so it's always a little bit difficult to wrap your head around. But if we not look at just an XYZ coordinate system, but also as an R, so R is then along the direction of the scattering vector. Theta is the so-called polar scattering angle, is the angle between the plus Z axis and the R direction, and phi is then the angle between the plus Z axis and the projection of the R axis onto the XY plane. We can use that. We can make that coordinate transformation. And since we had only a general, not very quantified expression for s squared yet, instead of writing it in terms of the unit vectors in the incident or scattering direction, we can also write it as a function of the angles theta and phi. That is the good thing of the transformation to the spherical coordinate system. Of course, in the spherical coordinate system, we can also define an element dA on a spherical surface. This figure is blatantly stolen from Wikipedia, so you can look at that there. But the surface area on a sphere in the spherical coordinate systems is r squared sine theta d theta d phi, and that we can put in our integral. So this integral, where we had dA in a coordinate system that was not yet defined, can now be written in a spherical coordinate system as such. So with r, so the dA is replaced with r squared sine theta d theta d phi. This function s that described how the light was directed is now still generally written in terms of theta and phi, and not anymore in the unit vectors. And this is just a improduct of two unit vectors, so that will end up as a cosine. The net result is this. Oh no, that will not end up as a cosine, because as the scattered wave and the way we are looking at through the surface of the sphere are always aligned. So this one will actually evaluate to 1 in all cases. So then in spherical coordinates, then the integral becomes this. So we have an integral over from 0 to 2 pi d phi, and from 0 to pi sine theta d theta, of whatever is the argument of that integral. I'm assuming a little bit here that you have seen these kind of integrals before, but yeah. All right. Okay, then we're almost there, because the top expression gave us the relation between the scattered power and the incident power. The equation that is just below that makes it rather easy to rearrange. So the final expression that we have for the scattering cross section now here is this. So 1 over k squared, and then this double integral over two coordinates. Easy, right? Okay, the important. This is a little bit of. So it's not a very satisfying result, because you cannot calculate anything from this yet. The important takeaway points here are now that the information about all the information about the scattering process is contained in this function S squared. So it tells you how much light will be scattered, and because it defines the scattering coefficient, and it tells you the direction in which it will be scattered. So all the information is there. So the strength and the redirection of the light. A few final steps before the break. But the main result is already here. It is sometimes convenient to split these two effects. So sometimes you just want to have a number that tells you how much light is scattered, and sometimes you just want to have a number that tells you something about the redistribution. So to split that into quantities. So let's take that equation. Rearrange by taking k squared to the other side. Quite doable. And then just simply define a new function. Define a new function. P of theta and phi is equal to a normalized version of s squared. So s squared was the function that held all the information. But if you now take take this function and just normalize it on the whole angular domain, then you will get only the angular properties in that function. This one has a name. It's called the phase function. That function hails from astronomy, coincidentally, but relates to phases of the moon. But still. It contains only the information on the redistribution of the light, so not how much light is scattered, but in what direction. It is normalized function, as you can see by the definition. So it's normalized on the spherical domain. So different ways of saying that it is normalized on solid angle theta. Another way of saying that it is normalized on over the integral of 0 to 2 pi of d phi and 0 to pi sin theta d theta. And another interpretation that we'll get, I will not dwell on that too much today, is that you can interpret it as a probability density of scattering into a given name. But we'll get that's for later. So now if we have this normalization, then by definition, we should have that one equals the integral of the phase function over that whole domain. And using that, we can write it. We can try to insert it back into an equation for the scattering cross section. So we have now here the scattering cross section is equal to the scattering cross section times the integral of this phase function, and that is really a bit of a trivial approach because of that normalization. So we are allowed to write this, and then we can define a new quantity called the differential scattering cross section that finally separates the strength of the scattering in a quantity here. Maybe the other way around. So we have a quantity here that differential scattering cross section that defines both strength of scattering and the angular dependence, and that is a product of the total strength of scattering and the redirectional parameters. Very often there will be no dependence on phi in such a phase function, so there will be a lot of spherical symmetry. So that means that one of these two integrals you basically do not have to do. So that will just reduce to a factor of 2 pi. Let's just. I have a few more slides, but most of these are just pictures. So bear with me for a little moment, and then we'll have another break. such a function, like a phase function, is not it's not really easy to work with because you have a whole function and you would rather just have a number. So we can define the average of the cosine of the scattering angle. The average of, yeah, it does get a little bit complicated, that's true. The average of the cosine of the scattering angle as a measure for how the light is redirected. So you can imagine that if so do you have any feeling for what it would mean if so we had a polar scattering angle and an azimuthal scattering angle. So let's say there is not much dependence on the azimuthal scattering angle because that is averaged out. So the polar scattering is the only one that is important. So what would it mean if the polar scattering angle would be 0? Yeah, all the light would go straight through.
Yeah.
If the polar scattering angle would be 180 degrees, then everything would be scattered back.
It's relative to the incident.
Yeah, because of this spherical geometry, it is now relative to the incident direction, and that means that this average of the cosine is actually a good measure of which way the light goes. You can also interpret it then as a measure of the amount of light that is still traveling in the forward direction after a number of scattering events, so after interactions. So if theta is small, that means a small angle, then the g will be close to 1. So if you have a g value that is close to 1, then a lot of light will be scattered in the forward direction. The caveat is so it does not mean that the cosine that the cosine of the averaged angle will be the same as the average of the cosine of the angle. So that you have to be a little bit careful about. But in general, what we have is that if g would be completely 1, that would mean that the average cosine of the scattering angle would be 1, which would mean that all the light is scattered in the forward direction. Likewise, if it is -1, then all the light would be scattered in the backward direction. And a little bit more complicated part is what g is 0 is. G is 0 means that the average of the cosine is 0, but that does not mean that all the cosines have to be 0. And so that could mean or that means that we have an equal amount of light that is scattered in the forward and in the backward direction, but it does not imply that it is scattered equally into all directions.
How can be -1 because your angle goes from 0 to 180 and the cosine is really from 1 to 0?
And 1 would be just the total backscattering direction.
No, but -1.
For the cosine? Goes from one to -1 back to 1. So oh yeah. I'm just going to give you, and that's the picture, the last few pictures before the break. A few pictures of phase functions of particles of different sizes. And different wavelengths or different particle size wavelength ratios. So what you'll see here on the horizontal axis is the scattering angle, so the angle into the polar angle into which light is scattered. Here you see the magnitude of the phase function, so not necessarily of the amount of light, but of the relative magnitude on a log scale. And here is a polar plot that shows the same function, but then on a polar plot. So for the polar plot, the light is incident in this direction, along the 180 degrees line, and then the red line shows a polar representation of the space function. So here you can see a particle where the radius is two times the wavelength. So the particle is much larger than and that results in light that is scattered predominantly in the forward direction. You can see that both in the blue plot, if you interpret the log scale correctly, because most of the light is around small angles theta. You can see it even more clearly in the bottle plot, where the light is also scattered predominantly in the direction where it came in. And you can also see it, infer it from the G value, from the average cosine of the scattering angle, which is really close to 1. So most of the light is in the forward direction. So let's make that particle a little bit smaller. So 1 times the radius. Well, you can see that the distribution of the scattered light is now much broader. It's in more angles, and again, both from the blue plot and from the red plot, but also from the G, which also gets the G value, which also gets a little bit smaller. It's still high, but it does show you that light is still scattered most in the forward direction, but is also redirected away a little bit. If we then make the particle half the wavelength, you see a more clear shift. So it is scattered more, not in the forward direction, but more around. Still predominantly forward. G value of 0.75, and the smallest particle would be a radius of only 1/10 of a wavelength. So almost equal amounts of light that are scattered into the forward hemisphere and into the backward hemisphere, G of 0.12, and a graph that shows no real modulations anymore. So the summary of these two functions, these two metrics for the phase function and scattering anisotropy, are that if we have as a rule of thumb, if we have a particle that is large compared to the wavelength, then we will have anisotropic scattering. So it is very angularly directed. So let's say in the forward direction here, with a G that is much larger than 0. If you would have a particle that is very small compared to the wavelength, then the scattering is much more isotropic, more in equal directions, and then G would be close to 0. And again, of course, that caveat. Even though we covered quite a lot of ground, we did kick the can down the road a little bit, because we still have not defined this magical function S squared of theta and phi, and we will need that in the end at some point in order to define the scattering efficiency, the cross section, the coefficients, and all the other properties that we talked about. So it's definitely time for a break now. And I'm going to think a little bit about how much information I'm going to feed you with, because I think it's a little bit overload. Huh?
It is.
Okay, so let's take if we say can you live with a 10-minute break and then half an hour of
I think we will survive.
Okay, let's do that then, and then because otherwise yeah.
In een van de laatste slides.
Kijken waar ik was.
Je één keer.
bij deze. Ja. Eigenlijk, als je hier zegt, dus als je het licht scattering events kijkt van grote particles, dan krijg je eigenlijk de meeste scattering is zeg maar het instant zo is dat scattering zie je het niet.
Ja, dat gewoon rechtuit.
Oké, maar het ramen bijvoorbeeld, want kijk ook naar scattering van maar in een ramenapparaat dan scatter je het dan instant staat in beneden en heb je je sample en dan kijk je naar de scattering wat allemaal omhoog gaat. Dus dan is je G-value is dan meest
Ja, dat klopt.
maar in wat voor situatie is dit dan? Want dan, dit is voor de situatie als zeg maar je licht groot of je particles groter is dan je licht. Toch?
Ja, dus een deeltjesgrootte die groter is dan de golflengte.
Precies, maar dat is, als je naar tissue kijkt bijvoorbeeld, dan is dat toch eigenlijk altijd zo.
Nou, niet helemaal. Als je naar een molecuul kijkt, zoals je een raam doet, dan is dat zeker niet zo.
Dus dan is zeg maar.
Ja, maar doe het dan gewoon.
Dus dan is meer een situatie zeg maar, als dit dan is, als je naar losse moleculen kijkt. Want dan is je molecuul natuurlijk kleiner dan je golflengte.
Zeker.
Dus dan krijg je, maar eigenlijk zou je dus, om efficiënter te zijn, zou je boven en beneden kunnen meten en meer scattering events mee te kunnen pakken.
Ja, maar het is wel wat wel zo is, en dat zie je ook dat zie je ook hier een beetje terug, is dat als je een meting in, dus dit 0 zou zijn licht wat gewoon rechtdoor gaat, en dit zou zijn licht wat in feite achteruit gaat. Het licht wat achteruit gaat, dat vang je op met een lens.
Ja.
Dus je meet in feite, je meet een aantal lichten daarmee. Dus je meet eigenlijk een redelijk groot deel van, je kan een groot deel van dit teruggaande stuk meten. En wat je wel ziet is dat als je nou verder naar die grotere deeltjes gaat, is dat hier steeds minder gebeurt. Ja, is hier ook niet heel spannend, maar je kan meestal uit de teruggaande richting wel meer informatie halen over het molecuul dan uit erheen gaan. Dus dat zijn nog. Ik denk dat een van de redenen is waarom het eigenlijk niet zoveel gebeurt om vooruit te kijken. Maar je hebt natuurlijk wel gelijk. In principe als je allebei pakt dan.
Ja, dat betekent fantastisch. Ja, maar. Maar we hebben er wel een rondje van, nog steeds uit 2 dagen voordat we op bezoek zijn. Oh shit. Heb je dat gehoord, die mensen hier? Ja, en het FVD-account van Zeeland dat deze jongeren ook maatschappelijk betrokken zijn en protesteren tegen de coronamaatregelen. Smaak is de vorm van een protest zeker niet, maar het gaat om de inhoud.
Dat zeg je ook alleen maar als je niet smaakvolle dingen doet. Dat is toch erg?
Dus wel bij dat week, weekend hebben we vrijdagavond. Dan wordt je dus een verjaardag vieren in de vorm van een barbecue. En nu kan ik gewoon braaf op die fietsje naar mijn kazee toe om daar te eten. Ja, omdat mijn broertje zodanig niet op mij lijkt dat ik gewoon niet meer naartoe ga. En ja, ook niet door het pad te vinden. Niet meer. Ik kom ook van expert die
dat is gewoon klein gezien.
Wat je daar puur op ziet. Maar dat zie je niet. Als je daar puur op staat, dan bijna niet. Alleen ze schaven de bovenkant al, daar is dan veel overheen, maar dan is het gewoon wat dikker.
Dit is echt wel de derde keer vandaag.
Onder zie je dat bobbeltje van die chips.
Ik ga even naar
Maar je ziet het bijna niet bij de anderen, alleen als je echt zo naar kijkt. En dan kijk je. En hij wordt ook meer van dat sommige mensen gaan er dus elke keer echt heel overheen doen in plaats van een keer weg. En dan wordt hij weer maar dat is dit vaak gewoon wegslijten.
levensgevaarlijk.
We hebben 50 zijn van huis koken.
Je moet wel goed sparen aan het. Ik ook. Dan.
Oh, ik dacht ook dat er totaal 2.
Ik snap het, maar ik bedoel, het is gewoon een typische wel grappig met
Best wel gedaan. Vorig jaar, enkele jaar. We hebben natuurlijk alles samen maken. Iedereen
Ik weet een beetje van buiten.
Wat is die daarvoor? Dus uithalen. Is dat
Ik ben geweldig geweest.
Hey, op middelbare school dan lijkt het ook niet. Ik een hele goede. Maar ik denk dat ik eigenlijk niks aan die dan waren andere opdrachten van ik heb een vriendin die heeft zijn kamer in Groningen.
Ik ben er een paar keer. Ik ben daar een paar keer geweest van die mensen van GLP. Dus echt inderdaad extreem weinig te betalen voor. Ja, oké. Maar ze krijgen ook echt heel blij van daar.
Ik ben er niet bij.
All right, guys. I've slimmed it down a little bit. I've slimmed it down a little bit, and I am going to turn some of it into a small homework assignment for you later on. But, dat is gewoon de consequentie. That's what you get home. This is nothing new. This is just, but I still chose to keep it here anyway. This is just to sum up what you did for now. So it says we have to look at different sizes, different scales in the tissue. So are we looking at vasculature, or looking at particles, or looking at dipoles? There was this long range of scales that were present in tissue, and we derived these general expressions for light scattering in tissue. So a few questions that remain is so particle forms come at different sizes, but what now actually determines the scattering properties, or the function S, of course, and then if we can determine the function S, is how can we calculate all these scattering cross sections, these phase functions, etc. It is instructive to look at different regimes. So, like we did with the phase function, where you already saw that there were quite some differences between when the particle was very small compared to the wavelength, or when it was very large compared to the wavelength. It's also convenient to do it here. So what I want to do here is fill up this graph. It's empty now. On the horizontal axis, we have particle radius. On the vertical axis, we have the scattering cross section. And if I'm not mistaken, all these calculations are done for a wavelength of 1 micrometer. So let's first look at the situation where the particle size is much smaller, than the wavelength. So that would be that range, for example. So up until cell membranes or something. So that would bring us basically back into the regime of Rayleigh scattering. That also was valid for the molecules in the sky, where the blue light scatters much more efficiently. The simplest way of describing it is in a classical picture. I'm not going to dwell too much on that because that will not have much. But the physical bottom line is that it results from the polarizability of the particles, and that basically means the ability how easy particles can form instantaneous dipoles. So how easily they can respond to the incident electric field. As that acts on the particles, these dipoles will start to oscillate. They will start to oscillate in phase, and that turns the particle as itself into a small radiating dipole, and that will mean that it will scatter light, that it will emit light. So in this case, and again, this is particles loosely defined that are much smaller than a wavelength. So you can think then of individual molecules or very small aggregates or very small solid particles. These kind of things. Of course, Rayleigh theory is quite famous, and as they did back in the day, they did not write it down mathematically, but they just started reasoning and then came to some conclusions. And he observed that the scattered field, so the amplitude, had to be proportional to the scatterer's volume. He observed that it had to be inversely proportional to the distance to the scatterer, so that it would emit a spherical wave. He observed that it should be time independent. I call that phase, no phase lag, no phase difference. So there is an instantaneous response. And he said it must be related to some kind of dimensionless function f that relates the input to the output. Well, that is the beauty of engineering, of course, because that is how the whole world works now. But, but then again, consequently, there had to be a square root relation, and then combining all these considerations, he could add up, he could end up defining some function f that was proportional to v, inversely proportional to r. He added wavelength, the stroke of brilliance, to make the whole thing dimensionless, and then ended up with a general expression that said that the scattering intensity is proportional to the particle size, to the sixth power, and inversely proportional to the wavelength, to the fourth power. And these are the hallmark characteristics of Rayleigh scattering. He derived it just by reasoning. I'll give you the expression of that scattering intensity at a distance r, and as a function of polar scattering angle theta. So there is again symmetry over the other scattering angle phi. That is why it is not in this equation. And you can see that there is there's a cosine squared dependence on the scattering angle. K to the fourth power means that K is 2 pi over lambda, 2 pi over the wavelength, so that is this inverse proportionality to wavelength to the fourth power. There is the polarizability alpha in there, which basically defines the aforementioned ease of the molecule, of the particles to form dipoles, and that you can write for a particle with radius a as such. So there is a refractive index in there, relative refractive index, meaning the ratio of the refractive index of the particle with its suspended medium that turns up both in the numerator and the denominator, and there is the particle volume in there with an a to the third term. So there's a lot of things going on in this equation, but eventually the things that Rayleigh derived end up here in this equation. Of course, as you can as you can imagine, I will ask something about this. So I'm just going to skip. It still works. So this is going to be your exercise. This is going to be your exercise for later. So if we now take that, I'll write it down a little bit better than this. If you take this general expression for the intensity of Rayleigh scattered light, can you then show that the phase function has exactly that expression? So with exactly that normalization. That is of course also at the same time, using the definition of the scattering anisotropy, can you show that that scattering anisotropy is for this Rayleigh phase function is equal to 0. But I'll write that down a little bit better. Yeah, so this as well. So if we use this formalism to calculate, I see that the wavelength was 500 nanometers here. If we use this formalism and calculate, for example, for a particle refractive index of 1.5, a medium refractive index of 1.3, do you have any idea, by the way, what refractive indexes for tissue-like materials are, or other materials?
Do you mean the values?
Yeah, the values, just ballpark numbers. I mean, of course, these are ballpark numbers, but
Above 1.
yeah, above 1, that's air, exactly. What is the refractive index of water?
1.33.
Yeah, 1.33. That would be spot on for something like 500 nanometer. Then it changes a little bit over wavelength. For most tissues, it's a little bit higher. That gives us contrast. So that's what you see here. 1.5 actually is a little bit of a high choice because that would be more like a glass.
The refractive index is dependent on the wavelength.
It depends on the wavelength. Yeah. Yeah. It generally decreases a little bit with wavelength. So if you would then plot, so using these numbers and the equation that we basically did not derive, You could plot the Rayleigh scattering cross-section as a function of particle radius, and then in bold here we have the only range where it is actually justified to use that approximation, because otherwise the particle radius would get too high compared to the wavelength, and then this is what you will get. So that's filling up part of the graph. So now let's look at the completely other side, where the particle is much larger than the wavelength. Really think nucleus size or cell size, red blood cell size. So intuition would tell us, I guess, that a large particle would block basically all the light. It would be reflected, but it would be, the efficiency would probably be 1, because all the light hitting it would be somehow redirected or so not such a bad expectation would be that the cross section, let's say the blocking cross section or the scattering cross section of that particle would be equal to the true cross section, geometrical cross section, or in other words, that the scattering efficiency would be 1. All the light would be scattered. That is partly true. So if you look at large particles like this one, so the first interaction mechanism is reflection. Light gets reflected. It doesn't have to be glass; it can be any other material, but some light is just reflected. Second mechanism is refraction. So light can, and that is what happens in the clouds, and when forming rainbows. If the light enters, this actually is a rainbow. If light enters the water particle, it is refracted in certain angles, and that also causes redirection of the light. So by definition, that also contributes to the scattering. But then there's a third process. Oh wait, not yet. So if you would only take into account these two processes, so either light is reflected from the particle surface, which means that it is not entering the particle, then that is one process. The part of the light that enters the particle is refracted, so that also interacts and gets redirected. Then this would be true. Then the sum of the reflected and the refracted power would be equal to the incident power, and then the efficiency would be 1. And if the efficiency is 1, then the cross section is equal to the geometrical cross section. So that would be just maybe as expected. There's one other phenomenon to consider. You all had it in high school. Reflection. There's also diffraction. That goes all the way back to Huygens principle. That if you would take a plane wave or a wave illuminating a small hole, you will see a redirection of the waves. You will see, and that happens for light as well. Of course, you will see a redirection of the light surrounding that hole. Each point in that hole will start as a new light source that will emanate a spherical wave, and all these spherical waves will interfere and form the next wavefront, and you will get this beautiful interference phenomena. So if you project that on the screen, for example, for a laser passing through a small hole, you would see something. You would see something like this.
So can I ask something?
Yeah.
How is this different from reflection?
Because refraction needs the particle. That is light really entering the particle, being bounced off inside, and then re-emitted again. And this is really, so there is no particle. There's only a hole.
We were talking about light that travels on a particle, right?
Yeah, but we'll get there.
Is this a particle wave duality?
No, it is just okay. Well, let's get a little bit forward then. So the bottom line of this is going to be that there is 3 effects contributing to light scattering. One is just reflection, basically bouncing off. One is refraction, like in the rainbow, and the third one is diffraction, like this one. And all these three components contribute to the total scattered wave. And they actually interfere. And it's really counterintuitive. I don't blame you for this.
But this can happen with the particle.
What will happen is, okay, let me finish the argument first, which it takes only one slide. So this happens, if you agree that this happens when you have a hole in the screen, then I'm going to say next is, so the scattering part I just said about, so that is fine. And now let's take a close look at this third interaction, that is diffraction contribution. Let's say you would take a screen with a hole, and you would look at the diffraction pattern, and you would take a complementary, so not a screen, a complementary particle, so it's just a cut out of the screen. If you then look at how the light the light propagates, you would expect that if you would have so the superposition of these two would suggest that the diffraction pattern of this particle is the same as the diffraction pattern of this hole. You're shaking your head in great disbelief. That is very good, because it is really hard to wrap your head around. So I can imagine you would say that if you would put the screen and you would put a hole, then you have no light at the other end completely. But okay, let me try to make this. Okay, I will try to make this argument a little bit stronger later on, if that is okay with you. But let's say this is at least the general idea that if a particle, I'm sorry, a screen with a hole of a given cross section produces a diffraction pattern, then a similarly sized particle will produce the same diffraction pattern. So that will cause the same removal of light from the beam as that particle. And of course, that is also going to be proportional just to the geometrical cross section. So that is going to add another efficiency factor of 1 to the problem, or to the. So basically, that means that if both the reflected plus refracted powers of the classical, let's say the intuitively understandable powers are equal to the incident power, and the power that is diffracted or incident or equal to the incident power, then the total scattering efficiency is going to be equal to, because you have 2 times the same contribution, and that would mean that the scattering cross section is going to be equal to 2 times the geometrical cross section. This is actually because it is so hard to wrap your head around it. It is actually called the extinction paradox. So it is not it is not trivial. But a large particle scatters twice the amount of power that is incident. What you have to keep in mind, though, is that this is really only a far field effect. So you will not. It is not as if you will see. If you have something sitting in a window, that it will block twice the amount of light that is incident on it. You can observe it in practice. For example, if you look at light from a distant star that is scattered by a comet that passes through its light, and then you will observe that the amount of light is scattered is twice the amount of light that is incident. So that would give you this second asymptotical line. So for small particles, we have Rayleigh scattering. For the large particles, we have geometrical scattering, where the cross section is 2 times the cross-sectional area. And I'm just assuming a sphere here. That would look like that. This would be the asymptotes of what we can expect. So then the final question is there something that works in between? Can we fill the gap? Actually, it turned out that we can do much more than fill the gap. We can use mean theory. That's the last dead guy I'm going to show today. Mean theory is a solution to Maxwell's equation in spherical boundary conditions. And the only thing that you have to do is to just assume that the horse is a sphere, because that simplifies the math. It simplifies the math into these equations, so that is a little bit hard. So really don't just look at these as an oddity. I don't expect you to do anything with this, just to know that it exists. Or if you might need to use it, then be happy to know that there are excellent web calculators that you can just fill in all the parameters of your experiment, and you can just calculate. You can calculate what comes out. This is the result. This is the result. So again, assuming that the particles are spherical, you see that it predicts both limits accurately, and also the not so intuitive limit of the geometrical scattering. So as long as we can assume that the horse is a sphere, we have the tools to calculate the scattering properties. Okay, and that is then my final point, because I've kept you for too long. I will make a short assignment from the Rayleigh stuff. The idea is that's not for a grade, so it is just for you to work on, to have, and also to get a little bit of an idea of the things that I can ask later on. So I would encourage you to make it. But,
will you discuss the answer next time, or will you give the answers online?
well, we can do all of that. So next time is Johannes on OCT, and you also have to prepare something for that. So I'm going to post that as well. So maybe I will post the answers, but skip discussing it to next time. That's roughly what it is. All right.
Ja.